Okay, section 3.8, Foundations of Math and Pre-Calculus 10, page 188, is factoring special polynomials. So, special, put a little quotation behind special. Everyone likes to feel special, and it's good to know that there are some polynomials in math that are special. All right, so how do we, let's take a look at some examples here. So, here's an example. If we have 2x plus 2 squared, you've seen this before, and of course, what you know not to do, this does not equal 4x squared plus 4, all right? I want you to take a really good look at this right here, okay? And if you ever catch yourself thinking that this is okay, I want you to give yourself a big slap, okay? Yes. No, just go ahead and hit yourself really hard. There you go. That's nice. Nice. Okay, this is not okay. Okay? The distributive property of math does not apply to exponents when you have multiple terms, okay? You see, I know what some of you are thinking. You're thinking this. Well, Mr. Maxwell, what about 2xy squared? That's the same, Mr. Maxwell, as 4x squared y squared. And that is absolutely true. However, bless you, this is a monomial, this is not a binomial, so this is okay. This is not okay. This does not distribute there. You cannot do that, okay? Let's make that red. Let's make it really mean looking, okay? Do not do that, okay? Can you just raise your right hand with me right now, everyone? Go ahead. Raise your right hand. Nice try, Abby. That's your left hand. Right hand. Thank you. Repeat after me, please. I promise.
I swear.
I promise. Come on. Are you being difficult? I promise.
I promise.
Never to expand.
Never to expand.
A binomial that is squared by simply squaring each term and thinking that's okay.
That's wrong.
So help me God. I solemnly swear.
Jesus Christ.
Or I will, slap myself. Where is it again? Let's see. Nice try. Okay. So you cannot do this. Okay, good. Let's, Let us then get rid of the riffraff here. Okay. We don't want to poison our mind by seeing this again. Okay. Whoa. Just G2. All right. What this does mean is this, 2x plus 2 times itself, right? That's what that means. And when we multiply that out, we get 4x squared plus 4x plus 4. That's what that equals. Okay? Let's do another one. X minus 3 squared. That actually is x minus 3 times x minus 3. And if you're getting quick at this and you can do the FOIL in your head, that's going to be x squared minus 6x plus 9. Okay? Anyone think they can do it that fast yet? In your brain? No? Nervous laughter? Okay. Anyways, let's do one more, just one more. Okay, let's do 3x minus 5 squared, which actually equals 3x minus 5 times 3x minus 5. And that equals 9x squared minus 25, right? Okay, you all should be slapping yourself or trying to slap me right now for thinking that's okay. That's not okay. Look at it. I just squared this and squared. Are you guys awake? That's not right. This is not right. So let's back up. That is not correct. You guys are sleeping, man. You're sleeping. This is 9x squared. What is it? Look at this. Quick FOIL. Minus 15x minus 15x minus 30x plus 25. What? Is that right or is that wrong? Do I need another slap or is this okay? Alright, are you sure? Alright, so let's just tidy this up a little bit. Erase. Now, watch very carefully. What do you notice about this term and this term? What do you notice about this term and this term? What do you notice about this term and this term? They are all what? Sorry? Positive, okay. What else? That's not what I'm going for. Sorry? I heard squares. They are all squares. They are all perfect squares. Okay? Just wait for me. Wait for it. Okay? They're all perfect squares. Do you see that? They are all perfect squares. X squared is a perfect square. What is it? X times X. 9x squared is a perfect square. That's 3x times 3x. All perfect squares. And it makes sense, doesn't it? Look at that. You're multiplying something times itself to get this one. You're multiplying, something times itself to get this one. That makes sense, right? So this is our first special polynomial, okay? It's a polynomial that looks like these ones, all right? That A have the first and last term in the trinomial are perfect squares. And the final one, which is maybe a little bit trickier to come up with, though, what's the square root of this one? It's 2x, right? What's the square root of this is 2, right? So what do you notice about this? Let's do it again. X square root of x squared is x. The square root of it is 9. Okay, is either positive 9 or minus 9, right? I'm sorry, square root 3. 3. Back that up. Hello. It's, 3, right? So you see these pairs here? What's the square root of this? This is 3x. What's the square root of this one? 5. Okay? So do you see how these are related? Okay. No one noticed this?
I did.
Did you? You did? You were just too scared? What should that be? 8. Thank you. Got too far ahead of myself. Yes, I made a mistake. Okay, congratulations. Slap me. Go ahead, slap me. All right, thank you. Thank you for that. Okay, this should be 8x. My bad. Why? Because 2x times 2x, and then you got 2x times 2, and you got 2x times 2. Okay? All right, so what do we notice about these pairs and about the middle terms? Okay, so that, and this, and this. So, yes, multiply and double. Thank you. Now, it is a little bit tough to tell whether the square root of 9 should be positive or negative 3, but look at this negative 6. So that's going to be a negative 3 that we multiplied together. But yes, exactly. It's this times this one times 2. It's this times 2. It's this times 2. All right? Sorry about that first example there. But yes, we have a pattern. So if you see a polynomial that has the first term and the last term squares, they're perfect squares, and you take the square root of this and the square root of this, multiply and double it, and if you get this, you have a special polynomial. All right? So that's the first one. So let's just summarize this. If you have a plus b squared, the factored version will always be a squared plus 2ab plus b squared. Okay? Good? This right here, if you recognize a trinomial that is in this pattern, it is called a perfect square trinomial. Perfect square trinomial. Why? Because we've got a binomial that is squared. So it is a perfect square. It's something multiplied by itself. So in this example here, does this appear to be could it be a perfect square trinomial? Could it be a special one? Well, what you look at is the first term and the last term, and are they perfect squares? Yes, they are. So you could go right here and you could say, okay, 2x, 3, and 3. Is this going to get me close is this combination going to get me 12 somehow? And you look and you say, well, 2 times 3 is 6, and 3 times 2 is 6, so guess what? Yeah, that's going to give me 12. Or you look at this and you say, okay, 2x times 3 times 2. Does this give me 12? And yeah, it does. 2 times 3 is 6, times 2 is 12x. Right? Is that right? Good? You get it? So I just did that one for you. Okay. What about this one here? Another one. 4 minus 20x plus 25x squared. This is written in reverse. Don't let it fool you. Okay. I want you to take 1 minute and go ahead and factor that, and I'll show you the answer in a minute. All right, let's just go through this. So what I did first was I checked if 4 and 25x squared seem to be perfect squares, and yes, they are. That's good. And then I look at the middle term here, 20, and I go square root of 4 is 2, square root of 25x squared is 5x. Multiply all these together, that times 2. I get 20x. That's the same term as the middle, so I'm good. So you go ahead and write your factors down there, write the 2 down there, write the 2 down there, and so on, 5x, 5x. And both these signs have to be the same too, right? It's a perfect square. When it comes time to checking this is your guess, and you go, okay, let's do a quick FOIL. That's 4 minus 10x minus 10x plus 25x. You get 4 minus 20x plus, squared, 25x squared. That's what we ended up with, right? Now you guys were saying what? You're saying that what happens if I put if you put a negative 2 there? Sorry. If you put a negative 2 plus 5, okay. So let's try that. Let's say you went right to here. You said, okay, perfect square trinomial. This could be negative 2 here as well. And 25x squared, that could be negative 5x. So this is what you did? Is that what you're saying? Okay, let's talk about, let's just finish this one. Okay, let's finish this one. So if you did this, if you said, hey, negatives times a negative could be a positive, and negative times negative could be a positive, that would be the same as negative 2 minus 5x, right, times itself. So you could say, hey, that could be true. That could be true. So let's try it. If you do a quick FOIL, then you get positive 4, right? You get positive 10x, you get positive 10x, and you get positive 25x squared. The problem is that this isn't the same as what you originally had, right? So if you tried this, then you would still have to, because when you square something, you have to realize that you get the same answer. It's always positive answer, whether this inside is positive or negative. So you got to make sure you expand it out. Now the third option that you guys came up with was you did, okay, get this right, you had negative 2 and then positive 5x, right? Okay, 5x, and you added these or subtracted them? You added them, okay. Well, if you did the FOIL here, what'd you get? You get 4 you would get minus 10x plus 25x squared, which that would give you your original polynomial as well. Okay? So, what does this mean? Does this mean that we did something wrong here, or could there possibly be two answers? And this kind of comes back to what I was just saying up here about this right here. If you had negative 2 plus 5x, and you squared it, you would get the exact same answer as if you squared 2 minus 5x. So let's substitute a value in. I want to show you this. So let's say x was 3. So I'm going to substitute 3 in there, and this we'll get to the bottom of it, right? Let's see which one's right. So 2 minus 5 times 3 all squared is 2 minus 15 is what? Negative 13 squared, which is what? 169. Down here we have negative 2 plus 15 all squared, which is positive 13 squared, which is 169. So you see that you get the same answer when you check. All right. So we would have to have a little bit more information about the question to decide which factored form is exactly correct. So if you did, now this is kind of messy here, but if you had this as an answer for a factored form, that is totally correct. If you had this for an answer, that's correct as well, because it yields you the same answer. We would need a little bit more information to find out, which one of these would be correct, because we'd have to attach it to a real life problem. Okay. Like for example, if well, I won't give you an example. Forget it. We'll stop right there. All right, that's the first special polynomial. The second special polynomial we want to talk about today comes from this right here. If you have a plus b times a minus b, okay? If you have two binomials that have the exact same terms but different signs in the middle, one's plus, one's minus, when you expand this, you get a squared minus ab plus ab minus b squared. If you were gathering like terms here, because we have some like terms, a plus ab and a minus ab, they would cancel each other out. And so really what you're left with here is a squared minus b squared. So this right here is our second special polynomial. And does anyone know what this is called? Close.
Perfect square triangle.
No, that was the first one. No. See if you can find it in your textbook. It's in your textbook. What's it called? Thank you. Difference of squares. And it's pretty self-explanatory. A difference means subtraction. So we've got a subtraction in there between two terms. And squares are perfect squares. So this is a perfect square. This is a perfect square. So examples of perfect squares would be x squared minus 9. That's an example. 16y to the fourth minus 25. That's an example. If it can be written as a difference, and both terms are perfect squares, this one is also an example. Now you may be saying this looks like a sum, and it does look like a sum, like a adding, but because this is negative, this can be written as a difference, right? So really this is the same, and that looks more like a difference of squares. So what we want to do is we want to figure out, okay, if these are so special, why are they special? Why do we care? Well, it's because they're really easy to factor. because there's a pattern, right? You know that a difference of squares comes from factors that include the square roots, and the signs are always opposite, plus minus. So what do? We take this format and we just apply it. What's the square root of x? Squared is x. What's the square root of 9? 3. It's a difference, and that comes from a plus times a minus. So let's make 1 plus and 1 minus. And you're done. That's factored. The check looks like this. X squared minus 3x plus 3x minus 9, which is x squared minus 9. Checks out. Over here, looks like a difference of squares, so it should follow the same format. What's the square root of 16y to the 4th? 4y squared. What's the square root of 25? 5. So you put 5s at the end. Plus, minus, you're done. Over here, finally, looks like a difference of squares. 4, 4. The square root of a squared b squared would be what? Yeah, a times b. Plus, minus. You're done. So remember that whenever you see a difference of perfect squares, they always can be factored like this. Doesn't matter which one you show first, which factor, the subtraction or the addition, but that's your second special polynomial.